That's better. Okay, thank you for letting me know that I wasn't being heard. Okay, so now we're going to talk about FCore. Familial aggregation correlations. FCore, it estimates multivariate familial correlations and their asymptotic errors for all pair types. It estimates the equivalent count of independent pairs that could have been used to obtain the same standard error. It estimates correlations for subtypes and main types, and or both. And there's no limit on the number of traits. It uses all pairs of relatives where both members have data for at least one trait in common. It does not allow for covariate adjustment, but you can use derived variables using function in the GUI, possibly after determining appropriate covariate coefficients using S.A.G.E, which we will discuss later. So, take it away, Yunju.
Okay. The FCore is another program that, just like a pattern info, that needs just two default input files for S.A.G.E, which is the pedigree file and the parameter file. Okay, then it generates the INF file again, and one or more analysis result file depending on the output options specified. The first example, the example that we are gonna see is these options. We are gonna in these options. The trait will decide to analyze the first two, the factor A and factor 2. Okay, so we will have some cross correlations, which means like between the traits as well. And we will choose to analyze both main types and the subtypes, and we will report standard errors. By default, it does that, and we are gonna choose to actually output the smallest number of pairs used. Okay, if smallest number of pairs, one of the reasons that we want to do that is that if the smallest number of pairs used is less than, like, let's say 20, the standard errors may not be good. So it's good idea to actually check the pairs file. Okay, and oops, sorry about that. I clicked too fast. And we are gonna actually choose to run the homogeneity test jointly for all traits. This is the test of the hypothesis that all subtypes within a main type have the same correlations. You can have more detailed information about this test in the manual, page 140. Okay, let me go through the slide first, okay, and then I will show you Inline. So just like we just saw at for the pattern info, you can just click this analysis definition pane and then just click to those two factors, A, factor B, okay. And then we can specify whether subtype, main type, or the both. Okay, and then we gonna choose to estimate the standard errors and the output smallest number of pairs used. Okay, and this is by default right now. I don't think you need to actually choose that. But one thing that Dr. Harrison, I will go through this one, I think. Okay, before I actually showed you, or and maybe I will go. I think it's better to do this first. Okay. Unfortunately, the current GUI for the FCore actually reflects like all the options, especially in terms of like the output option block. Okay. So newer options choices are in the user manual. And the user can fix this problem by opening the parameter file, which I will show you shortly. And the subtype is default, and you can get out of it. So let me stop share. And I will share. The same screen that we were just looking at previously, okay? And then now we want to actually run the FCore, right? So we are going to choose FCore right here and then drop right there, job. Now it actually created a FCore job there. And now it says its data file is missing, just like before. So we're going to choose our data file, which is the schizophrenia data, okay? And then drag and drop right there. Now it is ready to go to the analysis definition pane, which you can do by next. Okay, and then in here, we will choose two traits that we decide to analyze, factor A, factor B. Okay, and then it estimates the standard errors, and then we want output smallest number of pairs used. Okay, and then we want both subtypes and main types, so we're going to choose the both. Okay, then once we start running, then that task pane, okay, but actually the parameter file will be, pop up analysis information that all the analysis, the options that we just choose. But right, just like the previous slide, as I was saying that, this option is actually reflecting the old options. So if we do it this way, it won't actually provide pairs file. So what we have to do, I mean, if you want to see, I can just show you that it won't have it. Okay. So what you want to do is actually, this is a new way, is to actually say, make like a new sublog within FCore block, say output underscore options, okay, with the curly brackets. And we don't want this. Okay, this is how you want to do it, so that we can actually have like a pairs output files. So you can just modify the analysis option that you just choose. Okay, and then okay, then it will just run. As you can see, the task file pops up, and also right under, you just show like this, but if you just drag and drop, you actually see the console as well, which like a many people, you just may not know that it actually gives you the everything that we've been running in this way. So console, the pane, the console window is actually under this task. Okay. So, okay, now we have this FCore. Okay, info files we chosen. Okay, output files. Now you see two output files. If we first click the INF file, you see the first 10 individual, first 10 like the data, okay? And then it shows the same of the constituent categories about the same information we got for the pet info. And then this one right here, the intra-class, I didn't talk about it when we were looking at the parameter file, intra-class weight and the inter-class weight, specifying this was like old options when we didn't have the options to when we didn't have the new feature of the calculating the optimal weights by Matthew and the Matthew et al. Paper. So since the new implementation, this option is invalid. So it will just pop up as just one of the information, but it won't do anything, just letting you know that that option was not used at all, since it is not needed anymore. Okay, and then so that was the information file. And then this is the main output files, okay, which Dr. Elston will go through the details of it later. And then this is the pair file that it shows the how many pairs was used in each correlation calculations like this. Okay, that is the live demo of the FCore, and I will stop share this and go back to slide.
Okay, are we going back to slide 41?
Yes.
41, yeah. Okay. So if we,
yeah.
oh, you just went through this, didn't you?
Yes. So we just talked about this one. So we are gonna go to 41 to the output.
Yep.
Yes.
So this is the newer output, and it tells you that you have 123 pedigrees, and you have 2 traits there, factor A and factor B. Now here's, you look at this legend, it'll say if something is not a correlation not estimable, you get blanks. If the pair count is equal or greater than 100,000, then you'll get these ampersands, and the standard errors is greater than or equal to 10, and all the pound signs equivalent pair count is greater than or equal to 10,000. And the standard error is calculated by setting at least one non-estimable required correlation to a value of 0. And notice it's in brackets. That's how you know that it did actually set to 0 something that couldn't be estimated. Now,
really?
So here we have the output for male and female self. Now, what you have to understand about it, these are intra-class correlations for subtypes. And for siblings, both intra and inter-class correlations are in the output, and they can be pooled. You'll notice that the number of pairs that could have been used to obtain the same standard error is 80, which is less than we actually have, I think. So let's look at the inter-class correlation. We have the columns are son and the rows are mother. And we can see that the correlation, you can see all the information there, the factor A and factor B. You can see the mother-son correlation is minus point. Let me see we've got the interclass correlation for subtypes is minus 0.3521. It's negative. And then what you notice is that the equivalent counts is larger than the counts that we actually had. And that often occurs for negative correlations. It arises because other correlations required to calculate the standard errors are negative. This often happens. It's sort of, if you had a positive correlation, then that would tell you things are not independent, so you don't have as much information. And you can contrast that with a negative correlation, which says, hey, in some sense, you have more information. They're not independent, they're negatively correlated. And so you, in a sense, have more information. And that's a bit peculiar, but that's the way it turns out.
Peculiar.
Hmm? What was that? Anybody want to ask a question or something? I can't. To repeat it, if you have a positive correlation, that means you don't have as many independent pairs equivalent. On the other hand, if it's a negative correlation, it goes the other way. It sort of suggests that in a sense you have more information than indicated by the number of pairs. So now we're going to look at the sibling subtypes pooled. There's brother, brother, sister, brother, and brother, sister. They are intra-class correlations for SIBs, all subtypes pooled. And we can see that the correlation is 0.1825 with a standard error of 0.0752 and a p-value of about 0.02. Now let's look at the parent-offspring correlation, and it's going to pool the father-son, mother-son, and mother-daughter, all subtypes pooled. And you can see, is there another pop-up? I can't remember. No, there wasn't. I'm sorry. But look at these subtypes pooled here. And, oh, this one is inter-class correlation for parent offspring, all subtypes pooled. Yep. And you've got the equivalent counts everywhere and the p-values. Let's go on to the next slide. Here you have the parent offspring pool, father, son, mother, daughter. Those are the ones that are available. There were no father-daughter ones. And you see the chi-squared for homogeneity among the subtypes is 3 with 8 degrees of freedom and a p-value of 0.91, suggesting there is no hint of heterogeneity. And then the second one, you see you have a chi-square of 0.65 with a p-value of 0.36. So again, the intraclass subtypes are not significantly different. So now if we continue with another output pair, this table is the smallest number of pairs used to calculate the required correlations for subtypes. And you can see that the in the top table, well, you've got the factor A is, and B, the smallest number is 3. And if you look at the bottom for father, son, you've got these numbers are quite small, and it's that you need those to get the correlation you're looking at. So it's a little bit suspicious with numbers as small as that. Okay, now we're going to talk about segregation models. First of all, we're going to talk about maximizing likelihoods. So all numerical methods start from a given set of initial values, and then what happens is after that, we start traversing the likelihood surface in different directions until either we meet a boundary or we meet a local maximum has been found, or numerical difficulties are encountered. Now, you can input the initial estimates, and sometimes it will help. However, you shouldn't ever input initial estimates unless you have a good reason to. For example, you may have an analysis with no covariates, and then you may want to add the covariates. Well, it's good to start the maximization where you left off with all the covariate values 0, and then it goes round and repeats it. It goes and maximizes everything all over again, bit by bit. Now, at this point, I want you to look at me, because I was once giving this talk, and it was Alec Wilson who was presenting this slide, and he had a sheet of paper. Now, watch carefully. I have crumpled it up, and he did that. And he said, this is the likelihood surface you are looking at. Now, I hope you will all remember that. Even in just 2 dimensions, this likelihood surface doesn't just have one maximum. It's all like a crumpled surface. You should remember that from now on. Okay. So we're going to, if you want to test hypotheses, you can compare two models by comparing their maximized likelihoods. And the larger the number of parameters over which there's been maximization, the larger the likelihood. A model can be determined to be significantly better than a submodel nested in it under certain conditions by comparing twice the natural log likelihood under the model minus twice the natural log likelihood under the, if you like, the hypothesis, the submodel. And you can compare that with percentiles of the chi-squared distribution under certain circumstances. Now, the number of degrees of freedom is the number of functionally independent constraints on the model implied by the submodel or hypothesis, or, which is exactly the same thing, the difference in the number of functionally independent parameters estimated in the two models. So, nesting of models is not necessary to perform such a likelihood ratio test. However, nesting and the following two further conditions are necessary for the chi-squared distribution to be appropriate. So you can always do a likelihood ratio test, but if you're going to start saying, oh, well, therefore I have a chi-squared distribution, you need something else. Firstly, you need large samples. And the question then is, how large is large? I had one of my professors tell me that maximum likelihood was stupid because you didn't know how large the sample had to be. Well, I can't tell you how large is large, but it's got to be pretty big. Now, the next thing is the submodel or null hypothesis must not be on the boundary of the model, which we can see here. You see, we can think of the model with a submodel in it. This is just 2 dimensions. If that submodel or hypothesis is on the boundary, then all bets are off, or at least there are ways of doing things there, but you can't just use the ordinary chi-squared distribution as such. So I want to talk now a little bit about AKAI's AIC. That's the A information criterion. It's a way of comparing nested or non-nested models without performing a significance test. You compare the likelihood values of minus twice the log likelihood. But if you do that directly, it's not very helpful because the log likelihood automatically increases when it is maximized over more parameters. So what you do is you penalize it. The AIC is calculated as minus twice the log likelihood plus the number of independent parameters estimated. And you can choose as best model the one for which the AIC is smallest. Now, you can read in the literature, and I can tell you that the AIC, the AKAI's A information criterion, is inconsistent, but it's pretty good. And the other thing I want to tell you, some of you know of the BIC, the Bayes information criterion. I maintain it should be always avoided. And the reason is, in my way of thinking, is because it penalizes you for having too large a sample. I cannot think of a worse idea. And I am not a theoretician, but I once talked to Sir David Cox, and he told me he would never, ever use the Bayes information criterion. And he was doing it on theoretical grounds. I don't know what theoretical grounds, but my argument is it is stupid to penalize yourself for having a larger model, a larger number of a larger sample size. All right. I want to talk a little bit about transforming the data. Let me see, here I am over here. So there are reasons for transforming the data. And according to what your reason is, should determine the transformation. If you do not want to confuse skewness with a mixture of distribution, use the Box and Cox transformation. On the other hand, if you want to just normality of the residuals, you should use the Georgian-Elston transformation. That's the Georgian-Elston modulus power transformation, sometimes known as GEMPT. Now, each of them has two parameters, a power parameter, lambda 1, and a shift parameter, lambda 2. Okay, so what you have to remember, and back in the, I think it was the 80s, the early 80s, there was a lot of argument about transforming the data and what it meant. And I remember there were papers in the American, I think the Journal of the American Statistical Association by Bickel and Dobson, and then there were replies by Box and Cox. I just thought the whole thing was a little bit stupid. You can read it all if you want, but the whole point is that if you take the likelihood of the transformed data on the assumption that the transformed data, for example, assumes normality of some genetic mean, you being some genotype and some variance for that genotype, that's not the same as the likelihood of the untransformed data, given the same transfer, the transformed data had this distribution. However, Andrew, for quantitative data, we choose the hypothesis and the transformation that gives the best likelihood, but the scales must be comparable. And that's all you have to remember, really, except with S.A.G.E, you don't even have to remember that, because provided the transformation is performed in S.A.G.E, we always calculate the likelihood of the untransformed data given it's transformed for the analysis. We do this automatically for you. This is the, let's consider now this, what our purpose. Suppose our purpose is to avoid the appearance of more than one distribution solely because of skewness. Then we will use the Box and Cox transformation. For y to be calculable in this Box and Cox transformation, x must be greater than -1 when lambda 2 is equal to 1. It's preferable to have it greater than equal to 0. Let's see what's going on in this transformation. Y as a function of x. What this is telling you is that when lambda 1, the power transformation, is less than 1, it spreads out the values, okay? Makes them, makes the small values smaller and the large values larger. On the other hand, if lambda 1 is greater than 1, it pulls them in, as you can see with those yellow arrows. No transformation is exactly the same as lambda 1 equals lambda 2 equals 1. You stick lambda 1 equal lambda 2 equal 1 in that transformation, and you see there's no transformation whatsoever. Okay? It will give you time to work it out. Now let's look at this, and actually this is from some actual data. So provided the transformation is done within S.A.G.E, all the resulting likelihoods are comparable. Now, supposing you get something like this. We will talk in a minute about a general model, a Mendelian model, and a non-Mendelian, if you like, no transmission at all. We shall talk about that. And here we see the maximum log likelihood plus some constant. The constant doesn't matter. That's the 1 over square root 2 pi. The constant's the same every time. So along the x-axis, we have the power transform lambda 1. And when lambda 1 is 0, that's exactly the same as the log transform. Excuse me a minute while I get on the same page on my other Okay, I still haven't got there yet. I'll get there in a minute. There it is. So now, what are you going to do? If you look at untransformed, when the power transformation is 1, you can see that the no transmission is very close to the general, the log likelihood, maximum log likelihood, suggesting that, hey, we should assume that is a better hypothesis than the one of Mendelian, which is way far away. On the other hand, if you look at the log transformation, now you can see the Mendelian is reasonably close to the general, but the no transmission is far away. So the question is, what are you going to do? Are you going to say this looks Mendelian, or it looks as though there's no transformation, there's no transmission whatsoever? Well, remember, you have to look at where the log likelihood, the transformation, you choose that one that gives you the best, the greatest likelihood. And you can see the likelihoods are all greatest when there is a log transformation at the 0. And under that transformation, you can see the Mendelian is really quite close to the general, whereas the no transformation is far away. So let us consider covariance. We, in S.A.G.E, all the means and all the variances can depend linearly on covariance. This is always possible. For example, for a quantitative trait y, S.A.G.E can transform both sides. Well, this is not an example, this is a statement, sorry. For a quantitative trait, S.A.G.E can transform both sides of any regression model. So you're taking a transformation of y, and the model says it has some beta genotypic effect for the ith individual. And then you've got all these covariates with the coefficients for that particular individual and a random error. So if it transforms both sides, it's rather clever what happens here, because when you do that, the result, the parameter estimates, other than variances, are median unbiased and on the original scale of measurement. And unfortunately, the variances are on the transformed scale, and there's reasons and complications caused by that. But when you transform both sides, whether you're doing a segregation analysis or association analysis, all the parameter estimates, other than the variances, are what are known as median. As the usual, when we say unbiased, we think mean unbiased. Well, these are median unbiased, and they're on the original scale of measurement, which makes life easy in terms of interpreting the results. You can get the variances on the untransformed scale, but with some difficulty outside S.A.G.E. And there are reasons for not putting it into S.A.G.E. I won't go into that now. All right, so let's consider some segregation models.
Actually, that was
it's lunch.
End of the second session that we worked by schedule. But if you would like to go more, or
we
only lunch, or
you mean it's lunchtime already?
Yeah, I mean, I think that we ended up about like a 15 minutes early again because there were no questions.
Well, let's see if we have some questions, because what I've said is you should probably ask some questions. If you have no questions, what can I do? You know, one of the reasons this is going so fast is because it's on Zoom. I heard someone just come on, but that's not the same as asking a question, is it? Oh, there's something in the chat I see.
I don't see any questions on the
don't?
chat. So...
Oh no, that's from before. Okay.
Yeah.
Yeah. So maybe you should digest transformations while you have your lunch. Any questions at all while we're onto it now? Okay, so we will reconvene at the lunchtime is what now?
Lunchtime is supposed to be 12:40 to
Oh, wow, as late as that.
1:20. Yeah, so we were supposed to resume back for session 3 at 1:20.
Yeah, okay.
Would
So
you like
let's,
to take
well,
about 2 hours of lunchtime?
well, that's what it looks like, because nobody will ask any questions. Joan's going to say something, maybe. No?
Yeah, I'm sure we'll have much more to say when we get into the meat of segregation analysis. But I did, just one thing for the people who've maybe never done this, because it's not, segregation analysis isn't being done as much these days, although I have seen some recent segregation analysis papers again. But for the young people, I mean, why did we do this? Well, we were doing segregation analyses before we had more than about 35 genetic variants that we could genotype across the genome. And we were trying to follow up on clinicians who would say, we really think there's something genetic going on. There's, familial aggregation, as FCore could tell you. Maybe you saw some correlation between relatives. And then segregation analysis was a tool that we could use to say, all right, if we think there are aggregated families, if we take a population-based sample, or at least a sample maybe ascertained on one case of a disease, for a quantitative trait, you could just take a random sample and then ask, is there any evidence, statistical evidence, not just eyeballing a few families, that there really are genes that have a big effect on the phenotype? And the reason I'm putting that into context is today, the most expensive part of that was collecting the family history information. Today, you could start to ask these questions again for traits out of electronic medical records, where you do perhaps have abilities to link families together. So that really expensive part is starting to maybe become possible again. And for some traits, it may be very useful to do this again. Yeah, Robert, would you like to comment on, why you would want to use segregation analysis?
Well, if you
today?
look back at the history, it's remarkable what we did do and find out. Now, I will say this, we will later on talk about linkage analysis. And if you have a good model for segregation, you can get a lot more information for your linkage analysis. And so that is well worthwhile. Yeah, you're absolutely right, Joan. The people didn't want to identify families and how they're related to each other. And yes, there is a paper. I'm a co-author, and I'm blanking on his on the first author's name. Some of you, if you see it, you can bring it up after lunch. But where from electronic family records, it's remarkable. You can with quite a good accuracy piece together families by knowing where people live, what household they're in, and their ages. Because if they're all in the same household and a bunch of them, two of them have similar ages and a bunch of the others have are about 20 years younger, you can assume that's a nuclear family. And it's remarkable how well that works. Do you, Jan, remember what the name of the senior author, the first author was? I can't remember. No, I can't remember. But,
I I think I know what you're talking about, so I'll find out shortly.
Okay. But I mean, it's remarkable what you can do these days. And this will give you much, much more power for what is now called positional cloning, which we shall measure, we shall talk about later on. As we'll talk about later on, positional cloning is just a fancy name for linkage analysis, which makes molecular geneticists happy, as far as I can tell. We'll talk about that. But the other thing you have to remember, there's a whole history of segregation analysis going back to about 1908. You've probably all heard of Weinberg for the Hardy-Weinberg equilibrium. Well, he was doing segregation analysis back about 1908, and until let's say about, I don't know, the 70s maybe, we always used nuclear families. Well, the thing is, you can have a lot more information if you have larger pedigrees. And one large pedigree, as I think we'll see in this course, one large pedigree can give you so much information, or two large pedigrees, twice as much, obviously. But it's segregation analysis, to my mind, is not dead. A lot of people think it's dead. I don't think it's dead at all. And people are using segregation models more with linkage analysis and getting more information. Of course, we'll talk about that. And I have a biased opinion. That's okay. I'm allowed to.
I agree with you, Robert. It's really, I think even if you yourself will never perform a segregation analysis, Robert's point that the model you pick in a parametric linkage can make a big difference in power.
Yes.
And understanding even the literature of segregation analyses that have been done for your trait of interest is really important. And so paying attention to what Robert's going to teach you about these models is critical, because you need to understand that so you can read that literature of all the work that's come before and use the best model that you can for your linkage study. Thank you, Robert.
Sure. Okay.
I can count on you to say the important stuff.
I will try at my age. So we will meet again. What time, Yunju?
Lunchtime ends at lunchtime goes until 1:20, so we will resume at 1:20. And for the one that you're looking for, is it Dr. Scott Hebring?
Yeah, yes, that's
yeah.
it. No, Scott Hebring. That's it, Hebring. Yeah, that's Hebring, or the 2B.
Yeah, Hebring. It's in the Marshfield.
No, that's not. It's Hebring. It's Hebring or Hebring. Yeah,
Hebring.
that's right. That's
yes.
right. It's Scott Hebring. Yeah,
yeah.
It's a remarkable paper. I became a co-author of it for I don't know why, but it really is a remarkable paper. Scott Hebring did a remarkable job on that. And it's amazing because we have all this information now. We've got all this electronic records, and to think that you can now, make pedigrees out of them. This is, I mean, there's a certain inaccuracy, but it's remarkable how accurate that is. And the thing is that nowadays, people are using segregation models in their other analyses more and more. And people are, they've learned how to do association analysis. They think they're genetic epidemiologists, but there's really not much genetic in terms of segregation, in terms of association analysis. That's really like case control and things like that, unless you have family data. And when you have family data, you can do wonderful things. Okay, so you said that what time, Yunju, you said?
1 penny. We will resume 1 penny.
1:20. Well, I'll probably be back about 1:15, so I can make sure I'm okay. Okay, so I'll see you back then. Thank you, everybody.